Okay, so in this video I'm going to run through paper 2 of the AQA Certificate in Chemistry of the iGCSE course. I'm going to go through it at a sort of reasonable speed. In an exam you've got, what is it, an hour and a half, so there's 90 marks, got 1 hour and a half to do this. I've no idea how long this is going to be, hopefully not that long. I'm going to go through start to finish, run through the questions to try and explain sort of what's meant. Paper 2 is a paper that concentrates on the practical elements of the chemistry, and so hopefully this will give you some insight into what kind of is expected of you and what's being asked. So use bits and pieces on the front, read all that information, but we're going to go on and make a start. So question 1 here is talking about saturated hydrocarbons. Blah 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 blah. Methane can be represented as this. Now, first question here that we're seeing is the formula of methane is what? Now, the formula is relating to methane, which is given to you here, so you're not going to learn anything. What we're told here is that we've got a carbon with 4 hydrogens, so the formula is simply CH4, and I'm just counting 1 C and 4 H's, and that's going to get me my mark there. Moving on, draw a ring around the correct answer and all this. They like this. Note that you only have to draw a ring around one answer on this. So in a saturated, this is an important bit here, saturated hydrocarbon molecule, all of the bonds are what? Well, the term saturated means single bonds really, so we draw a ring around that answer, and there we go, got ourselves another mark. So the start of this paper is quite an easy bit. The paper's geared so that the start is the easiest part, and it gets progressively harder, but within each question, the start of the question is the easiest part, and then it gets harder again. So we're always looking for it to get more difficult, basically. So the next one, complete combustion of petrol produces carbon dioxide, water vapour and sulphur dioxide. So what we've got here is we've got CO2, we've got H2O, and we've got, I lost what the pen is, there we go, SO2. So really what you've got to realise here is that in combustion things are reacting with oxygen, so there's a reaction with oxygen. So to produce carbon dioxide, carbon must be reacting with oxygen, so there's my first element. And to produce hydrogen oxide or dihydrogen oxide, H2O, the oxygen must be reacting with hydrogen. So we're not saying that it contains hydrogen atoms or molecules, we're saying that it contains hydrogen within the compound. Finally, sulphur dioxide, it therefore must contain, that's a terrible S, sulphur. So 3 reasonably easy marks there. Just looking at actually what is we've got there: carbon dioxide, water vapour and the sulphur dioxide. Sticking on a similar question here with fuels and all the rest, nitrogen oxides of nitrogen come from where? So where do we get the nitrogen from? Well, the nitrogen is going to come from air. So lost the pen, there we go. So we're talking nitrogen again, that's sort of making a majority of the air, 77-78%. Still sticking with fuels and the idea of pollution here, sulphur dioxide and oxides of nitrogen from cars cause an environmental problem. Basically, what is that problem and the effect of the problem? So the problem is acid rain, and that's just one you just really need to know. So acid rain is the issue. What's the effect? Well, you've got multitude of things. You could say damages trees or plants. You could say it's going to damage buildings, so we could say, obviously you need to just write one of these down, but it's a lot of answers. Damages buildings, trees, plants, kills fish due to being in lakes and all the rest of it. So a few answers there. There are several that you can have from the mark scheme, but that kind of, you've got certainly 4 there that you can choose. This one I like because it's talking about the incomplete combustion, but what it does throw in there is it says already that the one gaseous product of incomplete combustion is carbon monoxide. Name one solid product. At this point some people perhaps go straight away incomplete combustion and just put down carbon monoxide. That's already given. So one solid product is going to be carbon, because when we incompletely combust something, we basically have less and less oxygen. So in full combustion, say of methane, CH4 plus O2, we're going to get CO2 and H2O. CH4 plus O2. Hope this is all going to fit. Just these are basically the reactions that we're dealing with each time here, becoming progressively more incomplete or less complete. So balancing this up, we've got a 2 here, and we're going to need a 2 here, I believe. 2, 3, 4, yeah. Here we have got, still need the 2 here, we're going to need the 2 there as well at the end, and we are going to have 1.5 there, and finally just that 1 there. So you can see as we go less complete, the amount of oxygen reacting is decreasing, ultimately with the least being carbon being produced there. Still on question 1, still going. This again is quite a nice question because it's a data question. It's the analysis of data, so it's all based around this hypothesis. If a student is investigating how well different hydrocarbon fuels, that's quite important, just different hydrocarbon fuels would heat up 100 grams of water. And she makes the statement of the more carbon atoms there are in a molecule of any fuel, the better that fuel is. So she's talking about any fuel. Now straight away you should be realising she has not tested any fuel, she's just tested hydrocarbons. So instantly I'm thinking, well, that's not quite right, her statement is a little bit flawed, but nevertheless still not what the question's going to ask. Then we're given a table and it's these results, and the table gives you a range of hydrocarbons, alkanes. Going down here we can see that the carbon number is increasing, going from 5 through to 12 there. Then we're given the temperature change of water in Celsius after 2 minutes, and we can see that as we get the number of hydrocarbons increases, the temperature change after 2 minutes increases, which is excellent, but the temperature change per gram of fuel burned actually decreases. Finally, observations, we've got what you could say is quite clean, I guess, up this end, and then what you've got down here being dirty fuels. So what's the question actually asking? I've not even got to the question yet. So it gives me this again, it gives me the same hypothesis, and it's asking how well, at the top there, scroll up a little bit, how well, and use the results, how well do the student's results support her hypothesis? The more carbon atoms are in a molecule of any fuel, the better the fuel is. Well, my first thing would be student only tests alkanes. And we've seen that in the table we've got there. Pentane, hexane, octane, decane, and dodecane. So she's only testing alkanes or hydrocarbons, we could say. We're looking for 4 marks here, so 4 points to make, and we can see that down here. We're looking for those 4. Well, we've made 1 already, so we're looking for 3 other points to make, and those 3 we can take directly from this table. So I'd go first one, I'd look at, I've lost the pen, there it is, I'd look at this column here, and I'd say, well, actually, this column supports it. As the length increases, then we actually find that the temperature change after 2 minutes is greater. So, I've lost the pen again, there it is. After 2 minutes, the data shows the more carbon atoms equals greater temperature rise, therefore supporting, and this is supporting the hypothesis I'm talking here. So we've made now, we have made, I keep losing this blasted pen. There we go. We're looking for 2 more points to make. Well, again, sticking with the data, the next one along, temperature change per gram of fuel burned, well, that disagrees. So we're going to put that down. We're going to say that temperature change per gram decreased as carbon atoms. I'm going to start abbreviating this, so I don't want to start spending too long. And then the very final one, it's this idea at the side here, this one. And the key thing about this column here is that it's saying about the better fuel. Well, we're not necessarily even talking about energy here. We want fuels that are clean. We don't want to be burning fuels that release loads of smoke. So really, as the carbon atoms increase, it gets just pretty sort of rubbishy. It gets very, very dirty. So actually, that does not support the hypothesis. So Fuel gets dirtier as carbon atoms increase, and both of these ones then are not supporting. And there you go, you've got yourself a nice 4-mark answer there, which actually isn't too much. It's taking me long because I'm talking through it, but in your head shouldn't take you too long to get through there. We're still going with question 1 now. We're 6 pages in, and we're still on question 1. We're moving to a bit of calculation now, so it's quite early on in the paper here to get some calculations, but they're not too bad either. So, first bit here is calculate the number of moles of carbon dioxide produced. Well, moles, so you need to know there's a formula you need to know of this, and that's that moles equals mass over mR, or AR if we're dealing with elements, but we're dealing with compounds here. So we know that moles of CO2 is equal to the mass, so what mass have we got? Over 6.6 divided by CO2, so we're using these here to get the MR, we're going to add these together, so 12 add 16 times 2, which I know is 44. So basically the answer is 6.6 divided by 44, and that is going to be equal to 0.15. And so obviously we stick that down here. 1 mark for the working, 1 mark for the answer. If you mess the working up, you can still get the mark for the answer. Down here, same idea here. When the hydrocarbon was burned, 0.2 moles of water were produced. Okay, so 0.2 moles of water were produced. Now we know that water is H2O. So, how many moles of hydrogen atoms are there in 0.2 moles of water? Well, H2O, each mole of H2O contains 2 hydrogen atoms, so therefore there are 2 moles of hydrogen atoms in a mole of water. So, we take our 0.2, we times it by 2, and we get 0.40, giving us another mark. So 3 reasonably quick marks there. Now the next question is using those 2 there, so E part 1 and E part 2. And this is a bit of I think this is quite a tricky question. It's asking you to use that data basically to work out that, or to work out what the molecular formula of the hydrocarbon is, and we're using that data that's given. So the data basically is the 0.5, here we go, so we know carbon is 0.15, and we know that hydrogen is 0.4. And actually the way you do this is you just strike up a ratio between the 2. So carbon to hydrogen, 0.15 to 0.4. Now we want to get this to nice numbers really, so the problem we've got is that if we turn this down to say 1.5 to 4, well that ends up with C, 1.5 C's to 4 H's. Well, that doesn't work. So nice whole number. So the simplest whole number ratio here is going to be 3 to 8. And what that means then is we've got C3H8. And again, that's sort of thinking that's slightly outside the box kind of question there. But again, it's using the data involved, and actually it's the very last question. We've got a little mark box here. It's the last question of question 1. Therefore, we would expect it to be more difficult. And you can see we've got 19 marks worth here just on question 1 alone. But we're going to keep going. We're going to carry on. Next question, talking about salts now. So on to salts. Particularly, we're talking about a reaction here, so a precipitation reaction. Because we can see 2 solutions here, solution, aqueous, aqueous, and we can see that we make a solid. Therefore, this is straight away, I'm thinking, precipitation. Spelt right, I think. Precipitate, yeah. A bit of a method used there. Blah, blah, blah. Stick some things. You should be reading this slightly more clearly than I am. But I'm looking down and I'm going, oh, measure the depth in millimetres. I'm not going to do this one because I haven't got a ruler with me. And secondly, I'm reading it on a screen. And so it's slightly different to you getting on a paper, but you're just looking for this measurement here. So, measure. And then you write your answer here. It's got to be the easiest mark ever given on a paper. If you get that wrong, seriously, like, there's no helping you. The graph shows the students' results, next bit. I'll just scroll down here so we can see it. So we've got a graph of where we're looking at, we change the volume of potassium iodide. So what this reaction is we're adding potassium iodide here. Where have I lost my little marker? There it is. So we add, I've lost it again, there it is. We add this to this, and we get this thing produced, and we can measure the depth of this. That is the precipitate that's being formed there, the lead iodide. So, volume potassium iodide, we can see obviously that as this increases, so does the depth of precipitate up to a maximum point where it would plateau this bit here. So I don't know if they're going to ask me that in the question, but certainly I know that I want to be looking at the fact that as the volume of potassium iodide increases, so does the depth of precipitate up to a point, give that point, and then it plateaus. That's the way description of graphs works. But I can see down here, it doesn't look like they're going down that route. It looks like actually they're going down a route of looking at the anomalous points. So the anomalous points have been circled. Nice, thank you very much. There are some possible causes of anomalous results in the experiment, and they're given in this table. So for each possible cause given in the table, basically state what the effect would be on the depth of the precipitate formed. So if we had some water in the boiling tube before the solutions were added, what would that do to the depth of precipitate? Well, nothing really, is it? So same depth, and that's because if there's more water in there, you're going to find there's more solution in it, but it's not going to affect the depth of precipitate at all. Because actually when you look at this, just go up a second, you can see, honestly, where is this? There it is. This here is all some sort of solution, so there's just going to be a little bit more of that. There's not going to be more of this guy here though. A wider boiling tube was used. Well, if we use a wider boiling tube, you know, this versus this, then obviously that depth there is going to end up being much more shallow there. So less depth, and that one kind of makes sense. Again, this is a sort of a very thinking outside the box question. This is very paper 2. A shorter boiling tube of the same width. Well, the boiling tube's just shorter. It's not going to do anything. So same depth again. Finally, the boiling tube was allowed to stand for 2 minutes instead of 15 minutes. Now, I actually have a slight issue with this one. In my head, and the correct answer is, and this is one I gave this to some kids years ago, well not years ago, a year or two ago, and the real answer is greater depth. But I have an issue with that because in my head, if you allow it to stand for 2 minutes rather than 15 minutes, then less will have settled, therefore the precipitate will be, well, less. In my eyes, it should be less depth. But I think what they're saying is that at the point where you mix the two together, it would all look like precipitate, it would all appear as solid, and then eventually it would settle out. So I think it's a very dodgy question, and I really think it's a very poor question in fact. I would go less depth, and even though the mark scheme says greater, I would probably still go less, and I'd put myself out there on that one. So describe the relationship, oh there we go, describe the relationship on the graph, shown on the graph between the volume of potassium iodide solution and the depth of the precipitate. So exactly as we said, so if we look back up at the graph, as the volume of potassium iodide increases, then the depth of the precipitate also increases. And if we look at the numbers, let's pick a couple of numbers here. Let's pick something nice. Have we got any nice numbers? Let's look at the value for 2. So roughly there. So we've got 2, and we've got 5, 6, 7, 8. If we go to 4, it jumps to, hold on, 16. So let's use that. Let's say that, I've lost the pen, honestly, this is terrible. As volume of potassium increases, so does depth of, I'll abbreviate that to PPT, that's precipitate. Honestly, like, I cannot see where this pen has gone now. There it is. As one doubles, so does the other. Or you could say it's a linear relationship. And then finally, as I said to you, levels off at 8.8, just reading off of that graph, centimeters cubed of, and I'll abbreviate this to Ki, which is the potassium iodide. And there you've got your nice sort of 3 marks. That's quite a nice one. You should. This is the point in the middle here. This one. maybe a more difficult one to get. The other two, certainly you should just get straight away from that graph, and that's 2 marks out of the 3, if not getting that full 3 with the idea of the relationship between the two. How could the student... Oh, I liked this question back when we had it a couple of years ago. I like this question a lot because actually it gives you a lot of the detail. It says, how can the student obtain a dry sample of pure lead iodide from the mixture in one of the boiling tubes? Well, I know that in the diagram given there was this terribly drawn boiling tube, and this here was my solid, and this was some sort of liquid, a solution there. So first thing I'm going to do is I'm going to filter it. I can't do anything if I've not, unless I filter it. And then I'm getting, now I've got my potassium, my precipitate here. I filtered it, but is it pure? No, it's got all this solution around it. You know, you think about if you spill sort of Coke on your hands and you sort of wipe it off, even, or whatever, you've still got that sticky sort of, there's still that stuff there. So I need to wash it. I'm going to wash what I filtered, and I want it to be dry, therefore I'm going to leave it to evaporate. So we'll just say leave to evaporate. And this is the idea of the water that is being evaporated off, because I've washed it. I've now just got a damp sample. I'm leaving it to let the water evaporate off. 3 fairly easy marks. Actually, you don't have to say a lot there at all. 3 quite easy ones. State one use of a precipitation reaction. This is one of those you've just basically got to learn them. The one I like is water treatment, because that's the one that the lovely textbook seems to use. Quite an easy one there. Straight away done it. That's the end of end of question 2, with 12 more marks here. So we're 31 marks in. We're about a third of the way through the paper at this point. Still got plenty of way to go though, so pick up the pace a little bit. This one we're talking about, so it looks like seawater here, talking a bit about water. Right, it's probably from the air and water topic. So pure water can be obtained from seawater by, what's the method? Well, the method is distillation. Go down. What is the boiling point of pure water? You should know this one, hopefully. If you can find where the pen is, that is 100 degrees Celsius. Not too much of a difficult question. Nice couple of easy marks there. Again, at the start of the question, so they're more accessible for sort of the students who are going to attain more lower, basically. What piece of apparatus will be suitable for measuring? So we're looking at measuring here, but it's a giveaway. 25 centimeters cubed of seawater. We would use a measuring cylinder. Amazingly, that's not really a very difficult one. How could the student check that all the water had evaporated? I really like this question because it's a very, very practical based question. Almost sort of like, kind of thinks about sort of a A-level. Now what we need to look at is, the student is looking to see how much solid dissolves in the seawater. We've got to read back to these questions. Don't forget what the question is actually looking at. Student puts some water in an evaporating basin, measures the water into it, heats it, and then the water is evaporated, and then measures the mass of the evaporating basin. Now, if that student only heats for 3 seconds, obviously you could get mass, and the mass may have decreased. But to know that you've got just all the water evaporated, it's just a case of keeping heating. So keep heating, keep weighing, and what we're looking for is we're going to keep weighing until no further change. So we're constantly heating, reweighing, heating and reweighing until maybe after 5 or 6 minutes it remains at 4 grams or whatever it remains at. 3B then, still going on, 3B part 2. So we have got here a nice little calculation question. So the results the student obtained using 25 centimeters seawater are mass of empty evaporating basin as 23.21 grams, mass of evaporating basin and dry solid residue 24.04. Calculate the mass solid dissolved in 1000 centimeters cubed of seawater. Right, okay, I like that. Well, let's look first of all at what they got from 25 centimeters cubed. So we're given some data, so let's use it. So 24.04 minus 23.21, and that's going to give us a value. And ultimately, what we're going to be looking at there is it's the idea that if this is the evaporating basin, this is the evaporating basin plus the solid, then the difference between this two, which will be 0.83 grams, that's the mass in 25 centimeters cubed, but that's not what it's asking. It's asking for in 1,000 centimeters cubed. So we've got to multiply that up, and we've got to multiply that up by 40, and the end result here, the answer we're looking for, is 33.2 grams. So really, there's not very much learning that can be done about this in a lot of these questions so far. There's not as much learning as you would get in paper 1, not as much theory involved. A lot of it is just practical application of, in some ways, common knowledge. Why is chlorine added to drinking water? Classic question if you can find where the pen is. Kills bacteria. You could use microbes if you really fancy, but basically it kills bacteria. Don't say stupid things like makes it safe to drink. The mark scheme clearly says ignore that, okay? Be specific in your answers. It's not done to make it safe to drink, it's done specifically to kill bacteria, which in turn makes it safe to drink. So do be careful with the way you sort of answer your questions. Straight away, this little bit here, this tells me, before I've even seen the mark scheme, or seen the marks that I'm going to get, sorry, this tells me I have got a 6-mark question on the way. These seem a lot more scary than they actually are. It's about often using the data. Sometimes they're based on theory. Paper 2, quite often based on data that's given and getting you to evaluate things. So the data given here, we can see that we have graph 1. We have 3 graphs, graph 1, 2 and 3. So here's graph 1. It has age groups here versus percentage of teeth showing decay. And then we've got a little key here, water with fluoride ions, water without fluoride ions. So what do we get from this? Well, we see that clearly at all ages, water without fluoride ions gives more decay. Okay, so we get more decay at all age groups. Okay, much more decay. Most effective here, but it happens at all age groups there. And the graph 2, what's happening here? So graph 2 is showing us that we have concentration of fluoride ions in milligrams per 1,000 grams of water, and the percentage of children with decayed teeth. So what I'm looking, if I can find the pen, honestly this is impossible. There it is. Okay, so what have I got here? So first of all, I'm thinking, right, well, this is an important point for me right here, because this is the bit where we have the lowest percentage of children with decayed teeth. And I don't know what the question says yet. I'm just analysing the data before I even see it. So we can say at this point around about 2.5 milligrams of fluoride ions are most effective, and we can see that it's clear it's most effective there. And then obviously we can also see that from this region here through to this region down here, that the increasing concentration of fluoride ions actually causes a decrease in decayed teeth. Key thing is though, obviously up to this point that isn't an effective sort of a method. When you start to increase the concentration too high, it has no sort of, the impact is much reduced. So we're concentrating, could mean, I don't know what the question's going to ask, so it might be we have to use this data here along here, but I certainly think that this particular, that drop at the start and that lowest point are going to be important. Finally, graph 3, oh there's the pen, percentage of children with marked or brittle teeth, and we're looking at the concentration of fluoride ions in milligrams per 1,000 grams of water. So we've got 4 categories: less than 1.5 milligrams, 1.5 to 5, 5.1 to 12, and more than 12. So notice as well the types of graph they're giving you. The first one is a very comparative bar chart, line graph the second one, and again a bar chart here with these sort of distinct categories going on. What we're seeing here, well, clearly as fluoride ions increase, the percentage of children with marked or brittle teeth also increases. So that's obviously a key point, really. Question. Let's have a look. What's it asking us? So it's just asking us to evaluate the advantages and disadvantages of adding fluoride ions to drinking water. You should support your answer with evidence from all 3 graphs. What's important about this is by using all 3 graphs, actually that's where you score your 6 marks. You need no understanding of this topic at all. Important thing is that you must, absolutely must, in this kind of question, you must use good English. You must write nice sentences. You should think about what you're going to write. If it's all jumbled and rubbish, you're going to lose marks on it. It's got to be nice and clear. So you might write the greatest scientific answers known to man, but if it's not clear and it's not written well and it's not spelled well, which I know for some people is a problem, you're going to lose marks, and that's obviously a shame, but that's the nature of this kind of question. So, evaluate advantages and disadvantages. Well, look at advantages first off. It's about sort of stating the points here. So advantages are that, I mean, this first graph, graph 1, shows that, and I'm not going to write this one down just to save a little bit of time because obviously we've been through it. Advantages would be that as the ultimately adding fluoride ions from graph 1, adding fluoride ions to water causes a decrease in percentage of teeth showing decay. Important thing here, this is the greatest region here, and by making those 2 points you're actually going to score yourself 2 marks, which is quite nice. Graph 2, again we're making the points that were raised earlier on. Most effective, fluoride ions most effective, that 2.5 milligram-ish range would score you a 3rd mark. Down at this bottom one, sorry, I forgot where I was there. The disadvantages now, you could say that the increase in, or the use of fluoride ions causes, basically, or the increase in use of fluoride ions causes the children to get marked or brittle teeth, which is obviously a disadvantage. It's not a particularly useful thing. And then tying it together with a conclusion. And if you can do that well, also adding a little bit more detail into this graph here on the graph 2, particularly this start portion here, where we're talking about between 0 and roughly that 2.5 mark, between 2.0 and 2.5/3, that being the most effective. You can bring all those ideas together with a justified conclusion, because as soon as you see the term evaluate, although it doesn't specify here, you should be thinking conclusion. So you're evaluating the advantages and disadvantages. So you've got to bring in both sides of the argument. You must give advantages, you must give disadvantages. Ultimately though, you are looking to give a conclusion which is based on your opinion, but also obviously based on the data, and that's a very, very important thing. Put those ideas together, you're going to bust out 6 marks on this, and that 6 marks is really good to have. That's the end of question 3. On to question 4 now. Student investigated the reaction between magnesium metal and dilute hydrochloric acids. The student placed 25 centimeters cubed of dilute hydrochloric acid in a conical flask and set up the operations as shown in the diagram. Diagram here, we've got a little conical flask, we've got a reaction occurring in the bottom here between the acid and the magnesium metal, and we're collecting through here, into here, and into our gas syringe. We're collecting gas. In this case, that would be hydrogen gas collected. Now, bit of a methody sort of thing here as to what happens, how it works and all the rest of it. If you've never used a gas syringe, it's certainly worth reading this method because you might not know what's happening. So obviously the student has to take the bung out, has to add the acid, add the magnesium, starts a timer, and then records how much gas is collected in 1 minute, and it's shown on this graph. Now straight away I've got a graph in front of me and I've got a point which is clearly anomalous. So what are we going to do? Well, let's go down here. So we've got a question here on a symbol equation, no balancing involved. Instead we're looking for the state symbols. Now magnesium, you should have come across magnesium. Solid, it's a metal, we're already told that. Hydrogen gas, we know we're collecting the gas, it's in the gas cylinder thing. Final 2 here, aqueous. Acids are always aqueous. Magnesium chloride, metal salts, invariably aqueous as well. People trip out because they think this should be liquids, because they are liquids. They look like water or whatever. Liquids should only be used. L should only be used if you're dealing with water or a molten metal. So, for example, we could have iron. Liquid would tell me that it was molten at that point. Okay, so if ever something is a solution, certainly it's aqueous, AQ, it's dissolved in water, as opposed to L for liquid. So 2 nice marks for just doing the state symbols. This one, reading the piece of apparatus which is given, which is nice of them. So what volume has been collected after 1 minute? This is the gas syringe after 1 minute, which you can see in the question just there. So I'm reading this and I'm going 51, 2, 3, 4, 5. 1, 2, 3, 4. Oh, yeah, 55 I believe we've got there. 55 centimeters cubed. Next one, use the graph to determine the temperature of the acid used in this experiment. So I'm looking now at going up here, and where are we? We're looking at our volume of gas, and we had a volume of 55, so I'm going to go across there, right across here to that point there. I'm going to go down, 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 and I've got a nice point there, which is going to be 54 degrees Celsius. So 54 units are given to me in both of those questions, so I'm going to worry about that. Calculate the average rate of reaction in centimeters cubed of hydrogen made per second for this experiment. Well, we're still talking about this experiment right here, where we found that in 1 minute, which remember is 60 seconds, because we're looking to calculate this per second, we produced 55 centimeters cubed of gas. So that was in 60 seconds. Well, how many did we produce in 1 second? Well, in 1 second we did 55 divided by 60. So reasonably easy one. Obviously, if you've got a calculator, you stick that in and you're going to come out with 0.92 as your answer, which isn't too bad of a question to get hold of. Question 4 continues. Nice long questions on this one. We're getting our graph back again. So the student's graph has been reprinted to help with this question. Very nice of them. What's going to happen? So one of the results is on the graph is anomalous. Draw a circle. 1 mark for circling the anomalous point. Well, I wonder where it is. It's clearly that point there. You've just earned yourself a mark. Very, very easy mark. And this is a very, very good question, because it's asking what may have happened in order to cause, so suggest what may have happened to cause this anomalous result. Well, I'm looking up here and I'm thinking, well, in reality, this point should have either been there or it should have been there. So there's a couple of things that could have happened. I may find, first of all, maybe the temperature's been wrong. Maybe actually, it's been measured at the wrong temperature, or actually the gas has all gone a bit awry. Okay, because this should, in theory, be across in one of these situations here. So what we could find, if, for example, the volume of gas collected is correct, the student perhaps has written the temperature down wrong. Okay, so it was the temperature was recorded at something, whereas in reality the temperature was lower than that, which could give us a dodgy result. Or we could find that in this case here, less gas was basically produced. And I think this is the easy one to think about. Less gas was collected because actually the bung wasn't placed in or something. So an answer that actually gives you details as to why the value has dropped down. So the y is not where we would expect it to be. In both of those cases though, the answer that's given needs to have a little bit more detail. So if we stick with the one that gas was, we had a lower gas here, we would say something like bung not placed in correctly, and this is after we've added the acid and magnesium. And the thing with that is that leads to gas being lost, and that's the important bit. So it's not just bung not replaced correctly, it's that the gas is lost, and that is why it has been measured at a lower point there. If you want to go down the temperature route, then you can look at it the other way, and you could say something like temperature lower than recorded temperature therefore slower reaction. Personally, I've actually taken this one from the mark scheme to give you a couple of ones. I actually prefer this answer here. I've got to say, I think that's a much easier answer to understand. I find the other one actually a little bit confusing, and so I would go with the gas loss one because it's a much easier. And actually, you've probably done experiments similar to this, and if you don't get that bung placed in quickly, you do obviously get gas loss, which isn't ideal. So how could the student improve the accuracy of the volume of gas recorded at each temperature? How could the student improve the accuracy? Well, accuracy is the idea of reaching the true value. Now, there's nothing to say that actually the values that were recorded were actually correct. And we don't know that because we only do an experiment once. We're just taking the values and assuming they're right. So what he could do is he could have repeated. By repeating, it allows you to get a range of results, but that's not quite enough. When you repeat, you're then looking to spot anomalous results, but once we know that we have anomalous results, it's very, very important to identify, or we've already said about spotting them, exclude them from the data. And what I mean by that is because if we have a range of results, let's say we have 21, 22 and 34 as our three, whatever they are, volumes or times, whatever they are. This one is clearly a lot higher than the other, and therefore we're going to exclude it. When I calculate a mean, I'm going to calculate the mean of these two, divided by 2, and I'm going to, that's a 2, not a 3, and I'm going to come out with 21.5. So exclude them, and then obviously calculate. Oh, E went a bit wonky there. Calculate the mean. That's very, very important there. So exclude the value and calculate the mean. Classic kind of question. And question 4 still continues. We are still going. So this time, not looking at the temperature change, the student is using the same apparatus that measures the volume of gas produced every 10 seconds at 40 degrees Celsius. So he's every 10 seconds. He's got a point on the graph here. If I can find this pen, that would help. Boom, 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 etc., etc. Volume of gas collected. So there is a. This is quite a nice question because it's very, very, again, very, very practical based as you would expect from paper 2. But the practical is looking at the questions, looking at these given explanations, and then basically what's going to happen is they're going to get you to prove. Well, how could you prove each one of these? So the first explanation is there was a layer of, and this is to why it got faster over the 36 seconds, and we can see it's actually increasing there. So the first explanation is that there was a layer of magnesium oxide on the surface of magnesium. The layer of magnesium oxide prevented the magnesium reacting with the acid. As the magnesium oxide reacted slowly with the acid, the magnesium was exposed to the acid and hydrogen gas was produced. Second one, the reaction is exothermic, and so the temperature of the acid increased during the reaction. I like those. Very, very good. So we're split into 2 questions here, 2 marks and 2 marks. So what could we do in terms of explanation 1? Now that was the one that actually there's a coating of magnesium oxide. Well, these questions are actually a lot easier than they look. Remove the coating, amazingly, and if you've removed that coating, you can do it again, and then you can compare the results. And that's the key thing, is we're looking to compare results, and that's also going to be true in the next one. So this next one, we are going to. There's a couple of ones you could do here. Basically, you could. There's 2 ways to sort of attack this one. You could look at the question. The reaction is exothermic, and so the temperature of the acid increased during the reaction. Now, you could first of all say, well, I'm going to measure temperature before and after, and basically sort of, I guess, check what's happening there, and again compare results. Or, and I think I prefer this one in many ways, is try and keep that temperature as steady as you can. And the idea really of place, flask, in a water bath. The idea really that you're keeping this temperature the same, so that hopefully if there is an effect there from this exothermic reaction, that it's not really kind of going to be a particular issue. I've actually, if I want to remember where the pen is, this is actually a slightly different question. That this is actually the 2 marks here. Place flask in water bath. Sorry, in my head I confused this. Place flask in the water bath at a set temperature, and then compare the results. Or you've got this other option here, is the other answer for 2 marks. Measure the temperature before and after, and essentially you're just checking there to see if the temperature actually does increase, which would obviously agree that it is an exothermic reaction which is causing the acid to heat up. So 2 ways of looking at this, and 2 reasonably straightforward marks to pick up. Question 5. So we're getting through. We've not got that long until the end of the reaction now. End of the paper. So when ammonium chloride is dissolved in water, there is a temperature change. Water used. So we're adding different masses of ammonium chloride, and we're looking at the final temperature of the solution when it started at room temperature. So when ammonium chloride dissolves in water, the temperature change can be described as what? Well, the temperature goes down. We start at room temperature and we find that it goes down in each case, and we can see that from the results here. Clearly it's starting at room temperature, which we are not told, but obviously we can assume it's higher than 14.5 degrees, certainly it's higher than 1. So the reaction is endothermic, meaning that it takes energy in from the surroundings, and therefore the surroundings get colder and we feel that temperature change there. Give a reason for your answer. Well, just as I've actually just said there, the final temperature decreased. I was probably going to say after ammonium chloride added. Plenty of detail there, so they can't trick me out. Keep going, getting slightly harder now as we move into the question. The student added the ammonium chloride to the water and stirred the mixture. The water was in a glass beaker. His teacher said that using a glass beaker could cause inaccurate results. What could the student have used instead of a glass beaker to improve the accuracy? Give a reason why this would improve the accuracy of results. Right, excellent, good question. It's very, very practical, getting you to think about what you can do to improve a practical investigation. So, we're looking at a reaction where we're measuring temperature. So, the inaccuracy here the teacher's talking about is temperature loss, basically, because we're measuring a temperature. The only thing that you could have the inaccuracy would be with the temperature not being the temperature that it should be, and the reason could be because of heat loss or heat coming in, for example, in this one. So rather than using a glass beaker, we could use a polystyrene cup, just like you would get if you go and you get a cup of coffee or something. And really this is acting as an insulator, so anything that would insulate would be fine. You could just say an insulating material. It doesn't have to be a polystyrene cup. It's just, obviously that's a bit of an easier one that you've probably all come across. Reason, why would this have improved the accuracy of the results? Well, it acts as an insulator. And so what it's doing on this one, because we're looking at a temperature decrease, it's stopping energy, how can I word this, being gained, which would ultimately, if here's my beaker with my reaction occurring, if energy is gained, it moves in, then the temperature of this is going to increase and I'm going to get an inaccurate result. If this is a nice polystyrene cup, then the energy kind of just bounces off, if you like. It's probably a terrible analogy. Therefore the effect of the temperature here is due to the reaction, really, not due to anything coming in from outside. It's about as accurate as we can probably make it in a sort of in a lab situation, or a school lab certainly. The student made sure his investigation was a fair test. A bit unfair this, ironically. They don't like you using the term fair test, but they like to use it themselves. So obviously AQA just like to confuse you, which is nice of them. And so state 2 control variables the student should keep the same. Now, we're looking at temperature of water, or the temperature of the final solution, as we dissolve this ammonium chloride in it. So really, it's probably a good idea if we're dissolving in an amount of water. Probably control variable. Use, that's an E. Use same volume of water would be quite a useful one. Reason. Why is the reason for doing that? This pen just keeps disappearing. Bigger volume equals smaller. Oh, let's see. We'll start again with that one. Smaller temperature change. So that's one nice one there. Variable, another one, measuring temperature. So let's start at the same temperature. So starting, that is one word, just terrible. Don't know what my writing's doing in a minute. So starting temperature. Higher starting temperature, higher the final temperature, which is obviously not ideal. Because if you're just directly measuring the end temperature, you're not measuring the difference between the two. If it starts higher, it's going to end higher, and it's going to completely throw your results, really. I'm just going to leave it at those two. I think they're the two most obvious. Looking at the mark scheme, we've also got, I'm going to leave those. They're just a bit pointless, those other answers. I don't want them. So it's the table again, which is nice, but it looks like they've... No, it's the same table as before. Good. Repeated. That's nice. Plot the results in the grid. I'm not going to do this, but it's worth 2 marks. Okay, you basically just got to plot the results on the grid. You've got to do so carefully. Make sure you work out that each little one of these guys is 1, and each 2 of these is 1. So 1, 2, 3, 4, 5, whereas it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So just bear that in mind. The scale that's here, they've purposely used this scale here to throw you. So just be careful. The other one's a fairly easy one. I'm sure that does trick people out. So each one of those halves there on the side here, each one of these is actually 0.5 each box. Sorry, no, it's not. Yeah, it is. Sorry, yeah, it is 0.5. So now this isn't going to really work if I haven't drawn the graph here. Use the graph to estimate the temperature of the room. Complete the graph by drawing 2 straight lines of best fit through the points. So we've got the results there. Obviously we come to, right, okay, so we get to a point here where we have a plateau occurring. So we would expect to see, if I can probably just make this up, it's going to go, honestly, where is this pen? It's going to basically go down, and then it's going to go, and it's just going to hit a sort of blank. Not exactly at these points, that's just a really poorly drawn graph. So it's going to hit a plateau though. And the question is now basically saying, if I can work out where the pen's gone again, where is it there? Use the graph to estimate the temperature of the room. So let's have a look here. We are starting, and actually that was a very poorly drawn graph of mine, but I've kind of got to the point I need to get to. Your first value would be here, somewhere. That isn't the right point here, but I'm talking about this. It would be at this mass of 10, so it'd be somewhere on this line. So once you've got your results plotted, what you would do, is there a rubber on here? Yes, there is. Oh, there really is. Wow. Once you've got your lines, your points plotted, so let's say we put another one here and another one here and here or whatever. What you can do is you can draw in there a line of best fit that goes through those points. The end result being there that you can, it's a fancy word called extrapolation. So you're extrapolating the results back, in this case, to where we have 0 grams of ammonium chloride added. That therefore must be room temperature. So I don't know what the answer would be. Looking at the mark scheme here, we've got they expect to see a line drawn for the extrapolation, like I've sort of done there, and they're looking for a value around 20 or 21 here. So 20 to 21. You would obviously write one value, not all the rest. We've got a plateau though, so we had that end, we had that plateau phase there. We should be straighter than that. There we go. Explain why the final temperature was the same for all masses of 35 grams and greater. Straight away, you're thinking at that point, no more could dissolve. And I'm obviously talking about the ammonium chloride, but I'm cutting corners slightly, and that does say more. I can't even deal with that. No more could dissolve. No more ammonium chloride could dissolve. Therefore, no more heat absorbed. So this end idea, the endothermic reaction being there, the heat being drawn into it, the energy, which is what makes it cold when the dissolving occurs, energy is drawn in. That obviously cannot occur if it gets to a point where there is no more dissolving. So therefore no more energy change. Right, a second student also did one of the experiments. This student recorded a final temperature of 14.5. Both students dissolved 20 grams of ammonium chloride in water. Use the graph to explain the differences in the two final temperatures. So let's look at the values again. So a student found that when he dissolved 20, pen here, good. So student 1 got 8.5, which was the original one. Student 2 hit 14.5. Why is that the case? Well, he got a smaller temperature rise. Okay, or sorry, a smaller temperature decrease. Let's say we started at 25, he obviously got down to 8.5, he got to 14.5. So there could be that idea that it started at the same temperature, and really the only explanation there is that bigger volume of water used. And that would create, as we said earlier on when we looked at those sort of control variables, bigger volume of water used would lead us to a less accurate final temperature, in this case one that is obviously out by quite a bit. Other option is, again, with the same as our anomalous points earlier on, actually it's almost a repeated question. This guy could have started at a higher temperature, so he could have started at whatever 31 versus 25, and the same thing there would be that he had ended up with probably the same temperature decrease, but because we're only measuring the final temperature, we're not measuring a change in temperature, it's a fairly poor investigation, to be honest. But this guy here ends up with a value that is apparently much higher than this, but it needn't be an inaccurate way of doing things. It could just be that he started again with a bigger volume of water, therefore the overall energy, the overall heat change was less for the volume there, or it started at higher temperature. Either of those, and you don't need to give both because it's just one of them, and you're just giving one of those reasons and then explaining as we sort of have done in voice there. And that's the end there of question 5. I think we've probably got one last question now, and we're looking at acids, it looks like here. Yeah, so we've got, what colour would universal indicator change if solution, okay, so if we add some universal indicator to hydrochloric acid, basically what colour is it going to change? Red. Fairly easy. Good, 1 mark. How can a student show there are chloride ions? Well, classic test here from the analysis section. So what the student's going to do, he's going to, if I can find the pen, honestly, how many times I've said that now, it's ridiculous. Add silver nitrate, and we're looking for a white and precipitate. That's exactly the kind of question, actually, you could get that at A level. It's exactly the same concept again. Students love a good titration. So, results for titration can be used to find the concentration of an acid. 4-mark question here. Describe how to use the apparatus to do a titration using 25 centimeters cubed of dilute hydrochloric acid. And your answers should include how you determine the end point and how you can make it accurate. Good. So we're already told at this point to get people who say, oh, use a pipette and transfer 25 centimeters cubed, blah 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 blah, into a conical flask. It's a waste of time. You already got that, so don't bother starting saying all that. What we're looking for. Okay. First of all, we obviously need to react the acid with something. So what are we going to react it with? Well, we've got to name something. So let's say put sodium, and I'm just going to give it its chemical thing there, sodium hydroxide, NaOH, in burette. That's a starting point there. It's quite a good one. If we haven't got an alkali, and we need to name it, they're being quite pedantic at this point because we are later in the paper. If we don't react an alkali with it, really, we're not going to get no reaction. That's the sort of classic acid-base reaction in the titration we're looking at, which hopefully you will have done. How do we determine the end point of the titration? Now, it does say on here, and this is a tricky one, dilute hydrochloric acid, and it's got a few drops of phenolphthalein indicator. Now, they are giving you the indicator on this one. Now, you just need to know that phenolphthalein is basically colourless in acid. So at the point where it's in the conical flask with the HCl in the bottom, it's going to be colourless. So what we're going to do is we are going to add NaOH until, oh, it's a terrible T, just turns pink. That does say turns. No, kind of ferns, I don't know. That's really where the end point of the titration is here. So we've got to the end point, but we are not at the point where we're actually really, no idea of kind of accuracy in there. So how are we going to make sure it's accurate? Well, any sort of titration, what we're going to do is we're going to swirl as we add NaOH. These don't have to be written in this order. You can do it in some sort of nice little prosy bit. Add slowly, particularly towards what we would call the end point, towards where it turns pink. And you might say, well, how do you know where the end point is if you're trying to work it out? Well, you would often do a rough titration, which would tell you it was roughly 24, so you might blast it to 23 and then add drop by drop for that last sort of centimetre cubed and see a good accurate result there. And really that's what we're looking for. A couple of accuracy marks there. A few ones could be repeat the results. It's always good for accuracy. It's always a classic one. And I'm probably going to leave it there actually for accuracy wise. So you saw that again. So swirl, add slowly, and repeat. 5 potential marks there. They're only taking 2 of the accuracy marks there. I think we're getting there now. Hydrochloric acid is a strong acid. Ethanoic acid is a weak acid. Explain what is meant by the term weak acid. Really, it's just one of these sort of. It's very much a definition one. It's at this later point because it sounds really hard, but actually it's not. It basically it does not fully ionize, or we can use the term dissociate. Either of those is good. And what actually you would see here is ethanoic acid CH3COOH. It has this equilibrium set up where actually when we add it to water, out of every 1,000 or something of these molecules that there are, about 4 of them ish go that way. So actually it doesn't fully dissociate, whereas something like hydrochloric acid, you add it to water and it's like bam, everything just shoots that way, and it's this full dissociation or full ionization, and that's what makes it a strong acid, whereas this one here, bracket around there, is weak. So on the displayed formula of ethanoic acid is blah 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 blah. On the formula, draw a circle around the functional group in ethanoic acid. Right, this here, again, actually A level as well. That is the functional group. Oh, that's beautiful. That is the functional group for ethanoic acid, and as it is for any carboxylic acid. If this here was just an H, it would be methanoic acid, and still it would have that COOH, but obviously it's not. It has that little CH3 point drawn on there, so it's ethanoic acid instead. Or draw the displayed formula of ethyl ethanoate. This actually is a really easy question because there's only one ester, and it does state that here. Ethanoic acid, and you may have done a reaction like this. Ethanoic acid and ethanol react together to make the ester ethyl ethanoate. There's only one ester you need to know, and that is ethyl ethanoate. Do make sure you include all portions of the ester, all the correct number of hydrogens, so CH3, COO, CH2, CH3. Boom, 2 marks. And that is the end of the paper. Hope this has been of some help. If you've got any problems, do let me know. But yeah, thanks very much.